Hello, Matthews Gatos here. In this video, we're going to look at deriving power law. So the derivative of x to any real number exponent. Let's get started. Okay, I want to start just slow and kind of build our way up. So let's look at, first of all, what the derivative of f of x equal to 5 is. So I'm going to look at that graphically, and then I'm going to look at that algebraically. So graphically, we know that the derivative of any function is the slope of a tangent line. So f of x is equal to 5. That is just a horizontal line passing through the y value of 5. What do we know about horizontal lines? We know horizontal lines have a slope of 0. Therefore, if f of x is 5, we know that f prime of x is just going to be 0. So what I've shown you graphically is that the derivative of a constant is 0. Let's look at this algebraically with tangent definition number 2. So if k is any constant, I want to find the derivative of k and prove that it equals 0. So I have the limit as h approaches 0, f of x plus h minus f of x all over h. So this is going to be the limit as h approaches 0. Now f tells me I'm going to this function here, and I'm going to substitute x plus h into the variable. There is no variable, it is a constant, so f of x plus h is just k. Minus f of x, again, there's no variable to make a substitution. It stays constant, so that's just k. So I have k minus k over h. So this is the limit as h approaches 0 of k take away k is 0 over h, which is just the limit as h approaches 0 of 0. And I know from limits that the limit of a constant is just the constant itself. So I've shown you graphically and algebraically that the derivative of a constant is 0. Okay, let's look at a linear function that is an oblique line, so not a horizontal line. So what is the derivative of this function here? F of x is equal to 4x minus 3. So again, I am going to graph this line. I'm going to look at it graphically. So there is f of x, 4x minus 3. So you see a y-intercept at negative 3. And then I can find all the other points by using the slope of 4. Now remember, the derivative is just the slope of the tangent line. So we know in y equals mx plus b form, m is the leading coefficient, which is also the slope. So I can see, I know from 10c that that is my slope. Therefore, the derivative of 4x plus minus 3 is just equal to 4x. So I've shown you graphically that the derivative of a linear function is just its slope. Now let's look at this algebraically. So I want to say that y equals mx plus b is any linear function. So I want to find the derivative of that. Okay, so I'm going to look at, using tangent definition number 2, the limit as h approaches 0 of f of x plus h. So that's going to be m, my new x, and then plus b, minus my function f of x, which is mx plus b, all over h. So I have the limit as h approaches 0. Let's distribute that in. Mx plus mh plus b minus mx minus b all over h. So I have my mx take away mx, b take away b. So I'm left with the limit as h approaches 0 of mh all over h. And then I can see that my h's cancel, so that is the limit as h approaches 0 of m. And again, the limit of a constant value is just the constant itself. So I've proved algebraically that it is also equal to m. So the derivative of a linear function is just its slope. Now let's look at some other types. So we've looked at lines, now let's look at curves. So I want to use the limit definition to find the derivative of f of x equals x squared. So that's my function. So I'm going to look at the limit as h approaches 0 of, now f of x plus h tells me I'm going to substitute x plus h into my function. So it's going to be x plus h squared minus f of x, which is x squared all over h. So all I need to do is expand my function here. So x plus h squared is x squared plus 2xh plus h squared minus x squared all over h. So I see x squared take away x squared is gone. So I'm left with the limit as h approaches 0, 2xh plus h squared all over h. So in the numerator, I am going to factor an h, and I'm left with 2x plus h all over h. Cancel my h values. Just going to go up here, and then I'm left with the limit as h approaches 0 of 2x plus h. So I can sub it in now, so I have 2x plus h is 0, which is just 2x. So this is what the derivative is. Derivative is 2x. That's the slope of all tangent lines to that graph. Okay, now I'm going to put that aside for now. I'm going to do one more, and then we're going to kind of put it all together. So let's do a cubic function. Okay, so looking at this, if I want to find the derivative using tangent definition number 2, I'm going to look at the limit as h approaches 0 of x plus h cubed minus f of x. Okay, so I'm going to expand that x plus h cubed on the side here because that's a really big one. So x plus h multiplied by itself 3 times. So I'll do the first two, which I know is just x squared plus 2xh plus h squared, and then multiply that by x plus h. So I'm going to have x cubed plus x squared h plus 2x squared h plus 2xh squared plus xh squared plus h cubed. I just squeezed it in there. Okay, and this will all be over h. So f of x, actually I can fill that in there. I know that f of x is equal to x cubed. Okay, so limit as h approaches 0. Now let's take this here. So I've got x cubed. Let's see if we can combine any terms here. So I've got an x squared h and 2x squared h's. Altogether is 3x squared h's plus 2xh squared, and an xh squared is 3xh squared, and then an h cubed all over h. Now that is take away the x cubed. I almost forgot that. Okay, so x cubed, take away x cubed is gone, so I'm left with the limit as h approaches 0, 3x squared h plus 3xh squared plus h cubed all over h. So let's factor that common factor of h in the numerator. So then I'm left with 3x squared plus 3xh plus h squared all over h. So my h's cancel. So I'll just go over here. I'm left with the limit as h approaches 0, 3x squared plus 3xh plus h squared. So I'm ready to substitute in my h as 0. So I get 3x squared plus 3x times 0, h squared, 0 times 0 is 0. So really my derivative altogether is just 3x squared. Okay, a lot of work for such a simple little derivative. Let's kind of put it together though. So we already know the derivative of a constant is 0. The derivative of a linear is just the slope. Let's look at the x squared. So we had our function and the derivative was 2x to the exponent of 1. So just 2x, we didn't really need the 1. Look at what happened. What happened is we take this 2 and we brought it down, and then this exponent of 2 becomes 1 because I just reduced my exponent by 1. Let's see if the pattern works over here. So f of x was x cubed. Here is the derivative. So bring the 3 down. Yep. Decrease my exponent by 1. Yes. So I see a pattern here. So let's apply this pattern in general. So if I have a function f of x equals x exponent n, what is the derivative? So follow the pattern. Let's bring the exponent of n down. So n times x. Decrease your exponent by 1, n to the 1. So this gives way to the power rule. So if you have a function f of x, which is x to the exponent of n, the derivative is n times x to the exponent of n minus 1. So you bring the exponent down, multiply it by the function, and reduce your exponent by 1. Now this power rule works for any function in which x can be written as a power. So before the power rule, we had to do this limit. The limit as h approaches 0, f of x plus h minus f of x all over h. But I told you that limits give way to derivatives. So now you've seen a nice shortcut rule that we've proved using the limit definition. So basically, after I've taught you the power rule, that limit seems like it's worthless. Not entirely worthless, though, because limits do lead us to derivatives, and now you know what the power rule is. So if you liked this video, please give it a thumbs up and hit subscribe so I can help more mathies just like you. Thank you for watching, and I'll see you for the next one.